So we are going to talk about the hidden subgroup problem. Many of the problems that we have studied up till now, such as Simon's problem and order finding problem, can be reframed in the form of a hidden subgroup problem. So what is the hidden subgroup problem? We have a group G and we have some unknown subgroup H of G, and we have a function f going from G to some set X, which has the following properties. F of X is equal to f of Y if and only if X minus Y belongs to H, which means that the function is constant on the cosets of H. And our goal, so the hidden subgroup problem is the following. Given G and F with such a property, find the generator or the generator set of H. And we want to do that with the minimal number of queries to F. Now let's look at a few problems that can be reframed as the hidden subgroup problem. The first one is the Simon's problem. So Simon's problem. Recall that in the Simon's problem, we have a set and we have some numbers xn, and we have xi1 to equal to xi2 is equal to xi1 is equal to xi2 if and only if i1 plus i2, or there exists a hidden number s such that i1 plus s is equal to i2. And our goal is to find this hidden period s with calls to the database, which consists of x1 through xn. So n is equal to 2 power n over here. All right, let's look at how we can put this in the hidden subgroup problem as a hidden subgroup problem. So let G equal to Z2 to the power n, and we'll take H is 0s. And our function can be any function which goes from G or Z2 power n to a finite set X, which has the following property. F of X is equal to f of Y if and only if xo plus s is equal to y. Right, so you can see that this function is constant on the cosets of H. So suppose we have this is Z2n, this is the subgroup 0 comma s, this will be 1 comma s plus 1, and so on, right? So this could be so this is going to be the same on the cosets of. So this is some range x, and the function will be the same. And if we are able to evaluate the hidden subgroup H, we will know what the value of S is. Right, so that's the Simon's problem reframed as the hidden subgroup problem. Let's take a look at one more example, which is the order finding problem. So second, order finding. So recall what is the order finding problem. We have X belonging to Zn star. So Zn star is the group of integers modulo n, and the group consists of all those elements that are relatively prime to n, right? And the order finding problem is to find the period order of x. So find the smallest integer r such that x to the r is congruent to 1 mod n. So find r. This is the order finding problem. So how do we reframe this into the hidden subgroup problem? We'll take G to be the integers, actually the positive integers union 0. And we'll take f from such that f of a, so a belongs to G, is equal to x to the a mod n. So x, which is the range, will be essentially 0, sorry, not 0, but it will be 1x, x square. And then since r is the period of x, things will start repeating. So there'll be r elements in this x. Okay. So what will be the hidden subgroup H over here? We need f of a is equal to f of b. When will that happen? When x to the a is congruent to x to the b mod n. That means that a minus b, which is in this integer set, is congruent to, is equal to k times r. So the hidden subgroup H will have this property. So we have the, if I subtract one integer from the other, then it should be a multiple of r, right? So let me draw this picture for you. This is will be G, which will be Z. And the hidden subgroup is going to be our 0, R to R, and so on. And so the cosets are going to be 1, R plus 1, 2R plus 1, and so on. And then the set X will have, this will be 1, this will be X, and then X to the power R minus 1. Over here, the last one will be R minus 1, 2R minus 1, and so on. Right? So this will be, these are the cosets. And you can observe that if I take two elements from the same coset, then this property holds that if you subtract one from the other, then you get a multiple of R, right? So this will be the hidden subgroup. And if we solve this problem, we find the unknown subgroup H, which is basically essentially the subgroup generated by R under the plus addition. So once we get the hidden subgroup F, we will know R, right? So that is the hidden subgroup problem related to the order finding problem. Okay. Now, one final example is the discrete log problem. So discrete log problem. So what is the discrete log problem? Let's take a set C, which is equal to gamma to the j, where this j is equal to 0 through n minus 1. So we have these, you can again think of this as multiplication modulo n. So gamma belongs to, let's say, so this is gamma, and the discrete log problem is the following one. Suppose gamma is given and we have gamma to the A is equal to B. Okay, so we know this is known, gamma is known, and we have this B to be known. So both A and B are some integers in this set 0 to n minus 1. Then the question is, what is A? This is known as the discrete log problem, and it has got great applications in cryptography. And so let's frame this in the form of a hidden subgroup problem. And it is known classically, by the way, that this problem is quite hard to solve. So any solution to this problem, given gamma and B, the classically it's a hard problem to find A. So let's look at how we can frame this as a discrete log problem. So we'll take G is equal to Zn cross Zn. Okay. And we have F going from G to our set C, and we'll define F in the following way. F of x, y is equal to gamma to the x and b to the minus y. Okay, so now we have to find what is h. What will h be? So we know that f is same on the coset, so f of x1, y1. So we'll take x1 comma y1 as equal to some g1, and f of this is equal to f of x2 y2. When is this? And x2 y2 equal to g1 g2, where g1 comma g2 belong to capital G. So when are these two things equal? So let's plug in the value of the function. Gamma to the x1 b to the minus y1 is equal to gamma to the x2 b to the minus y2, right? But we know that b is equal to gamma to the a. So let's substitute that. So this will be gamma x1 gamma to the minus a y1 is equal to gamma x2 gamma to the minus a y2. So gamma x1 minus a y1 is equal to gamma x2 minus a y2. Right? So x1 minus a y1 is equal to x2 minus a y2, or x1 minus y1, x1 minus x2 is equal to a y1 minus y2. So we have that. And now if I have two elements, x1, y1, and if I take x1, y1 minus another element, x2, y2, then this is equal to x1 minus x2, comma y1 minus y2, right? But x1 minus x2 is a times y1 minus y2. So this is equal to a y1 minus y2, comma y1 minus y2, right? If f of x1, so if f of g1 is equal to f of g2, then we have um, g1 minus g2 is equal to a y1 minus y2, comma y1 minus y2. So what is this set? It's basically the set generated by a comma 1 belonging to Zn, comma, Zn. Right? So therefore, one can, if I determine um, the coset, we are able to determine this discrete log of over here. The discrete log A is such that gamma to the A is equal to B, right? So that's the discrete log problem. Now, all these problems, there are many problems, there are many more problems that can be reframed as the hidden subgroup problem. And it turns out that a quantum computer can solve the abelian hidden subgroup problem efficiently. But if I give it a non-abelian subgroup, it's not known that it can do that efficiently. However, um, uh, the abelian subgroup problem can be efficiently solved, which includes order finding and Simon's algorithm and so on. Right. Note that all the groups that we have studied were abelian subgroups. So it turns out that we can solve any abelian hidden subgroup problem efficiently on a quantum computer.